So now we're going to do a demo. I'm going to show you the Privacy Lab. I want to get into what the Privacy Lab is. And so I went through very quickly just now k-anonymity, differential privacy, homomorphic encryption, and provided a couple of examples that hopefully were helpful to showcase how they each actually work. And I would say that there's a lot of educational resources out in the wild, like white papers, explanations, etc., that have discussed each of these in detail. But one of the things that we hear quite frequently, especially within our industry, is that the reality is that many of us have actually had the opportunity to play with them. And so we don't know what the inputs look like, what comes out on the other side, or what you give up to get the privacy guarantee. So it's really difficult to think about how you can apply pets in our industry with our data if you don't have a place where you can sort of interact with them. And that's really what the purpose of the Privacy Lab is. And whenever I talk about the Privacy Lab, I always like to call it a playground because this is a place, this is a free resource for anyone who would like to use it in the tools portal. And here's where you can actually experiment with, for now, these three types of pets with real data. So you can do things like change parameters, see output change, and then start to understand and develop your own intuition on what some of the trade-offs are. So we'll start with anonymity. Okay, so this one, hopefully, as you saw with the earlier example, this is probably the most intuitive of the three, and it's also one of the ones that have been around the longest, definitely predates like our industry by decades, and the core idea is pretty simple. So before you share or use a data set, you're transforming it so that no individual row is unique. And right now, what I have here in the Privacy Lab is we've got K set to 10 and suppression set to 50. And the demo data, so within the Privacy Lab for each of these, we do have sample data, so just demo data. But you can also upload your own data as well if you'd like to see and experience what this will actually do to your own data set. And so the demo data included in this example is I would say like advertising specific event data. So we've got things like subscription purchase events with age, gender, region, etc. So I'm going to actually run this using these defaults set in here. Okay, so once I've run this, you can see here that what's happened is that exact ages, user data age here. I don't know if you guys can see my pointer, but under the column that says user data age, the exact ages are gone, right? It's been generalized into ranges, so 30 to 40, 40 to 50. The other thing you'll see here is that the specific promotion name and also the region are suppressed. They're replaced with the asterisk. And event type and gender are still there because they're lower in cardinality. They don't uniquely identify anyone. And so this is the fundamental difference from traditional analytics, right? Like traditional analytics, it's row by row, these individual records. K-anonymity operates on just the general shape of the data and is forcing the records to be indistinguishable from at least 9 others. And the output is still useful. You can see that subscription events, I mean, not if you calculated it, I don't know if you can see it visually, but generally, if you took a closer look at it, you can see that subscription events skew towards like the 30, 40 female segment as an example. So you can run sort of more of these aggregate analyses. And the key thing here is that you can't re-identify any individual in the data set. The other helpful thing I would say, in the Privacy Lab is we have these walkthroughs. And so if I look at the walkthrough, at k equals 1, this essentially means that there's no anonymization. And so you're going to get exact values. Age is 34 for this first row, for example. The region is shown. Every row is unique and identifiable. And so if we move K, and you can actually do this in the privacy lab if you wanted to. I'm showing you the walkthrough, but that slider works. And if we actually move the K slider to 5, now what you'll see is the age range, for example. So the exact values are gone. K anonymity guarantees that for any combination of values in the remaining columns, at least 5 rows will share that exact combination. And so really with this, what the trade-off is precision. So you're creating exact ages for age bands, and that's the negotiation at the heart of every pet, privacy versus analytical fidelity. And what K ultimately you choose depends on a lot of things, but things like your risk tolerance, data sensitivity. Higher K means stronger privacy, more generalization, less precision. So this is where you can play with this yourself on your own data sets and kind of see what level of K would make the most sense for your particular use case. All right, so now we will take a look at differential privacy. So where K anonymity was transforming the data set itself, differential privacy operates a little bit differently. It's protecting the query mechanism. If you can query a data set and get exact counts back, then by submitting enough clever queries like I showed in the example, you can mathematically reconstruct individual records. And so what differential privacy is doing is adding that calibrated mathematical noise to every query result. And the noise is meant to be large enough to protect any individual's contribution to the answer, but small enough that the aggregate picture is statistically valid. And the key parameter in differential privacy is epsilon. And you can think of epsilon as a privacy loss budget. So the lower the epsilon, the tighter the budget, more noise is included, stronger privacy. The higher the epsilon value, more budget, there's less noise, the answer and the result that you're going to get is closer to the truth. So this is set at epsilon value of 1, and I'm going to run differential privacy on a sample data set. Okay, and so this is what the output looks like. And we're looking at campaign conversion counts, 6 campaigns. So the non-differential privacy count on the left, this is the true count. And the differential privacy DP count is what differential privacy reports. And so for the red campaign, the real count is 80, but when you have applied differential privacy, what it's reporting is 63. So that's a difference of 17. If you look at yellows, same thing. The true count is 100. With this applied, 97, off by 3. So the noise is random. So some campaigns, as you'll notice, are going to be close, some are further off, right? Like a difference of 3 for the yellow campaign, not that big of a difference. But if you look at purple, for example, difference, or even blue, actually, difference of 94, 67. So the total, though, I mean, there's a kind of a difference because, again, we've got the epsilon set to 1, but it's in the ballpark. And the goal here is that the noise averages out at scale. And so this is sort of the fundamental difference from K anonymity. So it gives K anonymity gives you exact numbers on generalized data, but differential privacy gives you approximate numbers on real data. So I would say different tools for different problems. And if we take a look at the chart below, you can actually see the noise even more clearly, obviously, if you're taking a look at the bar chart. You can see that differential privacy is close to the truth and where it diverges. So at epsilon equals 1, which is what this tool has defaulted to, the privacy guarantee is strong, but the noise is, I would say, pretty significant. And so we can take a look at what happens when we actually relax that. Again, I'm going to do a walkthrough rather than risk trying to do a live demo of doing the sliders, but you guys can actually play with this after the fact on your own. And so if we set the epsilon to 5, the thing that you can see visually pretty easily at this point is that the orange bars, which is the differentially private result versus like no differential privacy applied, they're pretty close to the blue bars at this point. So stronger utility here, but ultimately weaker privacy, and you've spent more of your privacy budget. So this is the main parameter that you're negotiating when deploying differential privacy in a real system, and what epsilon is acceptable given like your specific regulatory environment, your data sensitivity, and the analytical precision of your use case. Like that's what I think is important for each organization to play with and understand and decide. And I will close out with differential privacy. And now we will get into the last one, homomorphic encryption. And so the problem that homomorphic encryption is solving for is that in every analytics or matching workflow, data has to be decrypted before it can be computed on. And the moment data is decrypted, even if it does so very briefly, even on a trusted server, it could be exposed. So there's a window of vulnerability there. And that's true whether you're doing, if we're talking about campaign measurement, if we're talking about audience matching, or even clean rooms. Homomorphic encryption eliminates that window completely because it lets you perform the computation I mentioned earlier, addition, multiplication, for example, directly on that encrypted data without ever having to decrypt it. And the result also, as I showed in the example earlier, is still encrypted, and only ultimately those who have the decryption keys can actually decrypt even the result set. So what I'm going to do is I'm going to run homomorphic encryption again on our sample data. And the thing you'll notice, I'm sure you're noticing, is that this is actually taking a little bit longer than the other two, and that's sort of the point. But the output here is purchase counts per campaign computed entirely on encrypted conversion data. So red is 38, orange is 45, et cetera, et cetera. And these are the exact correct counts. So I'm not showing you any comparisons because these are the exact counts of purchases. Homomorphic encryption isn't doing anything similar to differential privacy or k-anonymity, and that it's not adding noise, and it's also not generalizing it. So your answer is going to be mathematically exact. Gonna there it is. Went the wrong way. So as you can see in the bar chart, right, like if we look at no homomorphic encryption applied and homomorphic encryption applied, the bars are exactly the same. You're not trading precision for privacy in the way that you do with differential privacy. You're getting the exact answers. But as we noticed, as I was running this, it took a little bit longer to compute. And so that is really what the trade-off is in terms of leveraging homomorphic encryption. And what we have at the bottom is what we have is the reference workflow. So on unencrypted data, it took 0.425 seconds to do the calculation. On the encrypted workflow, it was 6.487 seconds. So that's like 14 times the compute overhead to perform that same operation on encrypted data. And so that is what your trade-off is when you're taking a look at homomorphic encryption. Privacy guarantee, exceptional, but really what you're paying, the way that you're paying for it is in compute. And so I think one of the things to consider is the amount of data that you're looking to do computations on. Because as you can imagine, the infrastructure cost could be very high. So that the privacy lab demo. And what I'm going to do now is stop sharing.